Good morning. My name is Octav Chipara. I'm an associate professor at the University of Iowa, and it is a pleasure to talk about some of the work that my collaborators and I have done on hearing aids and improving their performance by integrating them into the broader Internet of Things. Let me start by presenting some statistics regarding the prevalence of hearing loss to better understand the impact and the scale of this problem. In the United States, about 1 in 6 adults over the age of 18 report some trouble hearing. This adds up to approximately 37.5 million adults who have hearing problems. Worldwide, this problem is even more severe. The World Health Organization is projecting that by 2050, about 1 in 4 will have some sort of hearing problems. Hearing loss can have a profound and negative impact on one's quality of life. If it is left untreated, it can lead to social isolation, anxiety, and depression. Fortunately, we have already developed interventions that are effective in combating hearing loss. These interventions include hearing aids and cochlear implants, both of these devices being able to improve the lives of the millions of people who suffer from hearing loss. Despite having been shown to effectively combat the negative effects of hearing loss, hearing aids and cochlear implants are not widely deployed either worldwide or in the United States. In the United States specifically, only 1 in 4 of those adults who would benefit from using hearing aids actually can use them. A multitude of factors contribute to these problems. First, hearing aids tend to be expensive and often are not covered by insurance. We have an insufficient number of audiologists, which leads to significant barriers to accessing hearing care, particularly in the rural regions of the country. Finally, despite our best engineering efforts, about 40% of those who wear hearing aids are disappointed by their performance. At the University of Iowa, I work with my collaborator, Dr. Yushan Wu, and our students to answer 3 basic questions. How can we evaluate the performance of hearing aids in the real world? How can we develop hearing solutions that are affordable, accessible, and personalized to the needs of an individual user? And how can we build the next generation of hearing aids that will provide better performance and, as a consequence, will have better user satisfaction and compliance? Traditionally, hearing aids have been considered self-contained devices that operate in isolation. Over the past 2 decades, we have put a significant effort into developing better hardware and improving signal processing algorithms. However, I claim that if we are to continue to follow down this path, we should expect to see only marginal improvements in performance. My claim is that we need a change of strategy. Specifically, we need to consider these devices as part of a larger ecosystem of IoT devices that can be used to connect to the hearing aids and enhance their capabilities. In the remainder of this talk, we'll explore some of our first steps that we have taken down this pathway of integrating hearing aids into the IoT ecosystem. Since about 40% of hearing aid users complain about the performance of their hearing aids, it is essential that we understand the factors that contribute to user dissatisfaction. We could bring the subjects into the laboratory or into the clinic and ask them how have their hearing aids performed. However, this requires that subjects are able to accurately report and summarize their experiences. Usually, these reports contain little contextual information that could help us understand what factors contributed to the poor performance of the hearing aids. For example, if one tells us that they had problems with their hearing aids in a coffee shop where they met their friends, we would like to know what was the acoustic environment like. We would also want to know what kind of hearing aid features were turned on at that time. This information cannot be easily obtained either using clinical or laboratory-based methods or the traditional approach of collecting data in the real world using retrospective surveys. We wanted to develop a method to better answer some of these unknowns and do it in a way that imposed less burden on the user and enabled automatic data collection. Our goal was to collect data in the real world and in real time to shed light on the relationship between the auditory context in which users live their life, their perception, and the performance that hearing aids provide in those contexts. Furthermore, we also wanted to understand what is the auditory lifestyles of older adults. This could allow us to understand better what hearing aids they should be prescribed and discover new ways of personalizing the programming and configuration of hearing aids to better suit an individual's unique lifestyle. Our approach to addressing this challenge was to integrate hearing aids with mobile phones. We have developed a mobile phone application that would periodically deliver surveys in real time and in the real world. This approach is dubbed ecological momentary assessment and is more reliable than traditional survey methods because we are not asking subjects to either recall or summarize their experiences. We are asking them to tell us in the moment how their hearing aids are working and describe the context in which hearing aids are operating. We combine the user's subjective reports with data that we obtain from smartphone sensors and from the hearing aids, and we are able to create a detailed record of their experience. This information has helped us shed light on the interactions between auditory context, perception, and hearing aid performance. It has been almost a decade since the publication of the original work that described the mobile apps that we have developed. Those results showed that we can collect data reliably and that the data that we can collect can be used to make different kinds of inferences. Since then, we have used our mobile apps and techniques as part of numerous user studies. Here, I'm going to illustrate the broad applicability of our techniques by highlighting three different types of studies that we have carried out. First, we have used our techniques to better understand the auditory lifestyle of older adults. Specifically, we have understood what are the typical signal-to-noise ratios that they encounter during their daily activities. Second, we have used our techniques to compare the performance of hearing aids and understand which features provide the biggest performance benefits. This was made possible by the fact that our techniques provide an order of magnitude more data than traditional survey techniques. Finally, we have focused on evaluating ecological momentary assessment as a method of doing research in audiology. We have specifically evaluated its validity and reliability and identified the best situations in which it can be used. More recently, we have shifted our focus to the challenge of reducing the cost of hearing care and improving accessibility. One strategy to do so is to use over-the-counter hearing aids that have significantly lower cost than traditional hearing aids. The reason for the lower cost is that a traditional hearing aid usually comes bundled with several visits to the audiologists during which they tune the configuration of a hearing aid. However, in the case of over-the-counter hearing aids, it is up to the user to find their configuration. Needless to say that if the device is not configured appropriately, then it is likely that the user will not be satisfied with their performance and they are not going to use those devices. An ideal method for tuning over-the-counter hearing aids should meet three criteria. First of all, it should allow the user to personalize their device based on their hearing needs. Second, it should be accessible for users who are not technology savvy. This is particularly important for older adults who still find mobile technology quite difficult to use. Finally, the user interfaces that we use must be easy to use, and they must capture the feedback from the user in a robust manner. Before delving into the details of our approach, let me give you some background information on the standard process of fitting hearing aids. The process starts by having a patient come to the clinic to evaluate the severity of their hearing loss. This is accomplished by presenting tones at different frequencies and identifying the threshold volume at which the subjects stopped perceiving each one of the tones. The results of the evaluation are summarized as an audiogram. The audiogram is then used as input to what's called a fitting rationale, which uses population statistics and audiology knowledge to map it to a hearing aid configuration. This initial hearing aid configuration is then refined over the course of several visits to the audiologist based on feedback from the subject. The hearing aids that we consider provide preferential amplification on 8 channels, each channel controlling a different frequency band. The amplification that is provided in each channel changes depending on the input level. In total, there are 24 parameters that control the behavior of the hearing aid. For an over-the-counter hearing aid user, they would have to find the right configuration within this 24-dimensional space. We are literally talking about finding the proverbial needle in a haystack of 24 dimensions. Our approach to simplifying the configuration of over-the-counter hearing aids involves 2 steps. First, we take the 24-dimensional configuration space and we reduce it to only 15 discrete presets. Then, we use a personalization algorithm that obtains feedback from the user to select the one preset that the users prefer the most. The question we posed is whether it is possible to reduce this large 24-dimensional space into a handful of representative presets. We have done this by using an enhanced database which is maintained by the CDC. This database includes audiograms that are representative of the US population who suffers from hearing loss. First, we limited our scope only to those subjects who suffer from mild to moderate hearing loss and are good candidates for over-the-counter hearing aids. Then, we have used a clustering approach to identify configurations that are similar. Here, on the figure on the right, I am plotting the original configuration for each one of the subjects in the database as a black dot, and the red dots indicate the clusters that have been determined for the case when we are having 15 presets, one preset per cluster. The surprising result of this approach is that a small number of presets, it's actually sufficient to cover a large fraction of the configurations. Specifically, we say that a configuration is covered if it is within plus minus 5 dB of a preset. If we are looking at the coverage for when we are using 15 presets, we find that 84% of the input configurations would be covered with these 15 presets, and this would be sufficient to provide a reasonable configuration for 84% of the users who suffer from mild to moderate hearing loss. Now, we don't have to worry about the complicated 24-dimensional space anymore. It is sufficient to only find the best preset among the 15 presets that we have selected. To this end, we have a machine learning algorithm that proposes different comparisons between presets. The user provides their feedback regarding which one they prefer, and over time the machine learning algorithm will incorporate the user's feedback to identify the configuration that the users prefer the most. Our machine learning algorithms are able to use feedback from pairwise comparisons to quickly identify the feedback that the user preferred the most within a small number of pairwise comparisons. I would like to conclude by pointing towards the future. So far, we have taken hearing aids that operated in isolation, and we have integrated them with mobile phones. This level of integration has allowed us to better understand the interplay between auditory context, hearing configuration, and the performance that hearing aids provide. Mobile phones also are a great platform for personalizing over-the-counter hearing aids. However, this is just the beginning. We are at the beginning of this journey. Integration with other devices will open new opportunities. For example, when watching a movie, it would be better to directly stream the movie from the TV rather than relying on the hearing aid's microphone to capture the sound. The sound captured by the hearing aid is subject to the room's acoustics and other sources of interference. Further enhancements could be achieved also by integrating with other IoT devices. For example, you don't have to be within the listening range of a doorbell to receive a notification. An internet-enabled doorbell could directly deliver a notification to a user that can be displayed and presented to the user on their hearing aid. Finally, the biggest forthcoming transformation will happen when hearing aids will be able to offload code and computation onto edge and cloud services. This will open new opportunities to deploy more sophisticated signal processing algorithms that today cannot be deployed due to the significant resource and energy constraints of hearing aid devices. In conclusion, I would like to thank my collaborator Yushan Wu and also all our students and postdoctoral fellows that have been working on our projects. Thank you very much, and at this point I would like to take any questions that you may have.